Ever wonder how AI models, like the ones used in self-driving cars, actually learn?
Well, it all boils down to something called an optimizer.
And today we're taking a deep dive into one of the most popular ones, Adam.
That's right. And what's interesting about Atom is it's been widely used in machine learning since it was first introduced.
Back in 2015, right?
Yeah, you would think after all this time with new advancements in AI, something else would come along, but Atom is still a favorite.
It's true. And we're going straight to the source for this deep dive, exploring excerpts from the original 2015 research paper. Now, I have to admit, when I tried to read through this thing, it's a little bit of a tough read.
It's pretty dense.
It's dense, right? Lots of equations, very technical, but luckily we have you here to guide us through it all.
Well, happy to help make sense of it all. So at a high level, Atom is used to find the best solution to a problem, right? So imagine you're an explorer and you're trying to find the lowest point on like this constantly shifting landscape. This landscape, it represents the data that the AI has to sort through. And the lower you go on that landscape, the better the model is performing.
I see. So I'm picturing almost like sand dunes or something like that, constantly moving. So how does it handle that?
Well, you can think of Atom as this really smart explorer that can adapt to the changing terrain. So when the path seems clear, it can take big steps, it can move quickly, but when the terrain gets a little uncertain or bumpy, it knows to slow down and take smaller steps and analyze the surroundings.
So it's kind of like it's constantly checking in, getting that feedback and saying, okay, I need to slow down here. I can speed up here.
Yeah, exactly. And what makes it even more interesting is it doesn't treat all parts of the problem the same way.
Okay.
It's like it's wearing, custom hiking boots on each leg
Oh, wow.
that are tailored for the specific terrain. So in technical terms, each one of these parts of the problem is called a parameter. And what Atom does is it can adjust the learning rate for each parameter individually.
So it's like it's analyzing each step as it takes it. Like, okay, for this parameter, I can go really fast.
Right.
For this one, I need to slow down.
Exactly. And this is especially helpful when we're dealing with what's called sparse gradients. So imagine you're analyzing a bunch of customer reviews
Okay.
to figure out, like the sentiment. Is it positive? Is it negative? Now, most of the words in those reviews aren't really going to give you much information about the sentiment.
Right.
Like the words the or a.
Those are filler words.
Yeah, exactly. And so this is where Atom's, ability to adjust to each parameter really shines because it can recognize, okay, these are the words that don't really give me much information.
So it doesn't waste time on those.
Exactly. And it can focus on the ones that are more meaningful.
So it's like our explorer is working smarter, not harder, by focusing on the parts of the map that really matter.
Exactly. And to help it navigate even more effectively, Atom uses a really interesting technique.
Okay, lay it on me.
It's called initialization bias correction.
Initialization bias correction. What in the world is that?
So as Atom is exploring this data landscape, it's building up like a memory, right? Like a history of its past experiences.
Okay.
And it uses that to make smarter decisions about where to go next.
So it's like taking notes along the way and referring back to them.
Exactly. But at the very beginning, its memory is empty.
Right.
It hasn't explored anything yet. So those initial steps it takes can be a little bit biased because it doesn't have that full picture.
So it's like starting a journey with a map that's completely blank.
Yeah.
It might take a few wrong turns at the beginning.
Right. And that's where bias correction comes in. It allows Atom to adjust, its understanding of the terrain as it goes.
Yeah.
So even if those first few steps are a little bit off, it can quickly correct itself.
That's interesting. So it's like it's constantly learning and adapting.
Exactly. And the paper actually goes into a lot of detail about the math behind all of this, like how it handles those sparse gradients. But the main point is it's designed to be really efficient.
Okay, so we've got this smart explorer. It can adapt. It can correct itself.
Yeah.
But the paper also talks a lot about the theory behind it, right?
Yeah.
So is that just to prove mathematically that it's as good as it seems in practice?
Well, yeah, they really wanted to understand not just that it worked well, but why it worked well.
Okay.
And what they found was, really impressive. Like they were able to show that it learns quickly, it's efficient, even in those environments that are constantly changing.
So it's not just a fluke. It's like they've got the receipts to prove it.
Exactly. It's built on a solid foundation.
So we have this smart explorer. It adapts. It's got the math to back it up. But is it the be-all, end-all of optimizers?
Well, that's a great question. And to be honest, even the researchers were a little bit cautious about saying, this is it, we've reached the peak.
So you're saying that even Atom has its limitations.
Well, remember how we talked about it building up this memory of its past experiences? Well, the paper hints that the way it estimates those experiences might not always be perfect,
Oh.
especially when you're dealing with very complex models. Like, think about image recognition or natural language processing.
Oh, wow. Yeah. Very complex stuff.
Adam's memory, it might not be completely accurate in those situations.
It's like even the best explorer can misinterpret a landmark every now and then.
Exactly. And so this idea, that maybe there are even better ways to estimate those past experiences, it really opens up a lot of possibilities for future research.
It's like we've climbed one mountain and now we can see a whole mountain range just waiting to be explored.
That's a really good analogy because this paper, it's not just about explaining how Adam works.
Yeah,
It's really an invitation to keep pushing the boundaries of what's possible.
I love that. So to kind of wrap up our deep dive into the world of Atom, what are some of the key takeaways that you hope our listeners walk away with?
Well, first and foremost, I want people to understand just how groundbreaking Adam's adaptive nature really is, this ability to kind of adjust on the fly, tailoring its approach to each part of the problem.
It's like having a super smart assistant who can just tweak all the settings for you.
Yeah, exactly. And secondly, we talked about those custom hiking boots.
Right.
The ability to handle these sparse gradients. It's like,
Mm.
you're sifting through this mountain of data and focusing only on the gold nuggets.
Right, which is important when these data sets are just getting larger and larger,
Exactly.
more complex.
And then finally, I want listeners to see Adam not as like this, isolated breakthrough,
Okay.
but as part of this lineage,
Okay.
building upon all these other great ideas like RMSProp, AdaGrad.
It's like standing on the shoulders of giants, right?
Exactly. And who knows what other amazing optimizers are out there just waiting to be discovered.
It's an exciting time to be following all of this.
Absolutely.
Well, a huge thank you to you for joining us today and for guiding us through all of this.
Happy to be here.
It's been a real pleasure. And to our listeners, as always, keep those brains engaged
And keep exploring those mountains.
because you might be the one to discover the next big breakthrough.
That's right.
Until next time.